Okay. So let's go ahead and start. So what we are going to do, let me go ahead and let me see. Review of Ohm's law. So we already did Ohm's law. Everyone, now last week, of course, we discussed about what you have to be careful when you're applying Ohm's law. Anybody remember? What did I say? Has to be potential difference. It should not be a potential on one side only. It has to be potential difference across the resistor that you must use. Remember that. Never make that mistake that Vs over R1. It has to be Vs minus whatever the voltage on the other side, or whatever voltage on the first side where the current is entering, minus the voltage where current is leaving. So that's, again, that's a common mistake, but I expect that you're not going to make that mistake again ever in your life. So just be careful about that. KVL, KCL, of course, everyone know about KVL, KCL. Anyone want to elaborate on KVL? Okay. All right, so if you have two loops, let's say you have voltage V1, you have voltage V2, you have some resistors R1, R2, R3, and let's say voltage VR1, voltage VR2, and voltage VR3. So if you're applying KVL in, let's say, loop 1, what will be your KVL equation? That is correct. So VR1 plus VR2, or in general, you can just add the voltages, go by the sign where current is either entering or current is leaving, and then you can just write down negative V1 plus VR1 plus VR2 is equal to 0, because sum of all the voltages around a loop, it is going to be 0. So you can just choose one direction in whichever direction you want to go, and then write down, and then sum up all the voltages in that direction. And those voltages that you are summing up should be equal to 0. So similarly for the second loop, you can go either clockwise direction or counterclockwise direction. It does not matter. So if I start with V2, then it will simply be V2 is equal to VR3 plus VR2, or negative V2 plus VR3 plus VR2 is equal to 0. Likewise, you can go clockwise direction in loop 2, and then you can have negative VR2, negative VR3 plus V2 is equal to 0, which will give you the same equation anyways, right? So KVL, simple. Sum of all the voltages around a loop is 0. Likewise, KCL, anytime you have a node and you have a bunch of things connected to the node, and you have multiple currents either coming or going from that node, then what, according to KCL, basically, how are you going to write the equation according to KCL at node A? What does KCL say? Exiting the node. Very good, excellent. So the sum of the current entering the node should be equal to sum of the current exiting the node. And the current direction, it does not matter, because when you're calculating in a circuit, you assign any direction of current. If the current direction comes out, if the value comes out to be negative, that means your assumed direction was opposite. So the value is correct, the direction is opposite. So it's totally random. Many times, of course, as an engineer, you already know in which direction current is going to flow based upon the power supply. But if you do not know, you don't have to worry about that. You just assume one direction, solve for that direction. If it is negative, that means your assumed direction was opposite. As simple as that. The value will still be correct. The direction is going to be opposite, like we did last week. and our current going into the source 2 was negative. That means the value is correct, but the current actually is coming out of the source. So in this case, if we apply KCL at node A, then we have two currents going towards I1 plus I2 and two currents going away. That should be, let's call this I4, I3 plus I4. So that's simply KCL. So that's KVL and KCL. Now with KVL and KCL, then you apply nodal analysis and mesh analysis based upon, first you write down the equation of KVL, then you basically perform Ohm's law. You apply Ohm's law on all the voltages to perform the mesh analysis. And for KCL, again, you write down the KCL equation first, and then you apply Ohm's law to find the node voltage, whatever unknown node voltage that you have. Oh, this was last page. What did I do? Okay, so let's go and let me copy this. Control A, Control X. What happened? I thought I created. Okay, anyways, let me create more pages. Okay, let's go to the first page now. And I'll just copy that. Why is this moving down to the last page? I don't understand. Control X. Okay, well, good enough. All right. So that is your KVL and KCL. Review of series and parallel resistive circuit. We know what is series, we know what is parallel, doesn't really matter. Anybody remember how you calculate the parallel equivalent resistance? Of course, we used MATLAB yesterday, but anybody remember for the parallel circuit, what is the parallel combination of resistance? How do you calculate it? One over R1 plus 1 over R2 plus 1 over Rn. That is correct. And series, of course, you add all of them together. So series is pretty simple. So make sure you have that function that you created during the software class. Or if you don't have that, just create another function in MATLAB, because that is going to be very helpful. As you saw last week when we were doing the problem, you saw I just use that function and then I don't have to do anything, using this formula, because the formula is inside the function. So keep that function with you. It will be very helpful because it will just cut down the time and any chances of error. Current division, something that we did again last time, not last week, I keep calling last week, on Monday, this week on Monday. And current division, I know Natasha said that she was always confused about current division. What is current division? So let's just do a quick review again, just to refresh. And I'm just gonna do 4 resistors. So if the total current is coming in, whatever the total current in is, and you want to find out the current through any of this resistor, then with the current division, how you are going to do that? Let's say I2. What will be I2? Who's gonna tell me? No, don't, just I2. What will be I2 expression using current division? Say it again. Uh-huh. The equivalent of all those resistors. Yes. Very good. Excellent. So the individual current, individual branch current, if all the resistors are connected in parallel, that's going to be the total current that is entering at that node, which will be, this current will be distributed among all these resistors. times the equivalent of all the resistor divided by the resistor value, which will be R2, through which you are trying to find the current. Now, just remember that this R equivalent is the parallel equivalent. It's not the series equivalent, of course, because the circuit is parallel circuit. So very simple current division equation. And you can see the relationship between current division and voltage division as far as the equation is concerned. In voltage division, you can find the voltage. If you know the total voltage and if all the resistors are connected in series, then you can find the voltage across a single resistor. And again, the derivation is through KVL and Ohm's law. So if, let's say, if you have 4 resistors and your total voltage is, let's say, Vs or Vt, whatever the voltage is, the total current will be Is. And if you want to know what is the voltage across R4, then anybody remember how I'm going to calculate the voltage across R4? Very good. Vs times the resistor across which you're trying to figure the voltage out divided by R equivalent. And again, this is R equivalent in series. So this is parallel R equivalent. So parallel, I just write down parallel actually. This is oops. And this is parallel R equivalent, and this is series R equivalent. So keep that in mind, just don't confuse them. But you can see the relationship between the two equations is basically you're making this reciprocal. Over there, total current times R equivalent over R2, and here, total voltage times the resistor divided by R equivalent. So they are reciprocal of each other. Okay, so we discussed voltage and current division, resistance combination. How to find node voltage? Okay, this is something that comes very handy. So node voltage calculation. Let's discuss this. Now, anytime you have a circuit, if you are an engineer, a technician, and you are working on a circuit, you're checking different spots, using voltmeter, different voltages and stuff. You need to understand how the voltage is going to be calculated at a specific node. Let's say you have, from a circuit, you have a branch. So let's assume that you have a resistor connected here, you have a battery, another resistor is coming here, battery, another resistor, and and let's say this is the node at which you want to find the voltage. Let's say this is node A. So this is part of a circuit. It's not a complete circuit, of course, but let's say a part of the circuit. And then this circuit, R1, let's say, is, and just keep it R1, I guess. And this is current I1 flowing here. Let's say this is battery V1. The current is, again, is coming here. And then again, as I said, it might be connected with some other part of the circuit, but let's say this is current I2 going at this node, and this is resistance R2, and this is battery V2. Let me change the polarity of this battery. Negative, positive. Let's do this. And someone asks you, hey, what is the voltage at node A? You already know, let's say in the circuit, you already know what is I1, you already know what is V2, I2, you already know the source voltages and stuff and the resistor values and whatever, right? So someone comes and someone asks you, calculate the node voltage at A. assuming you have all the other values. In a circuit, you can calculate with your ammeter what are the current flowing through different branches, you know the voltage values and all those things. And someone say, okay, well, you know all these values, how are you going to calculate, how are you going to determine what is the voltage at node A? So how are you going to do that? Yes. First, you need to know for what? You choose a reference. What is the reference you're going to choose? Okay, so you can choose a reference, any node at which for which you know the value of voltage. That can be any node for which you know the value of the voltage. The easiest thing, of course, is ground, because everyone knows that the ground voltage is 0, right? But if you know, hey, what is the voltage at this node, then you can choose this node as your reference, and you can start from there, basically. But ground is the easiest thing, since we know the value of the ground is 0. And then you start moving from the ground towards that node through any path, in this case, through this path, let's say. Now, every time you jump across a component, your voltage is either going to be dropped or it is going to be raised, based on the direction in which you are moving and based on the direction in which the current is moving through that component. So for example, I start with ground, the voltage is 0. When I move across R3 and get to this node, my voltage is going to be raised or it is going to be dropped. It is going to be dropped. Voltage always gets, especially the direction of the current is this, and it's the same direction in which I'm moving. So I'm moving in this direction. So I'm moving in this direction from the ground to node A. So I'm moving in this direction from the ground to node A. This is my destination, and this is my starting point. So I'm moving in the same direction current I2 is moving. And since voltage is dropped across R3 when current moves through R3, that means ground has higher potential than the voltage at this node right here. So what will be the voltage at this node? Negative I2 R3, very good. So that's going to be the voltage at this node. Let's call this node B. So we know what will be the voltage at that node. All right, we continue our journey. We pass through V2 and we get to, let's say, node C. Is the voltage going to be higher or lower? It is going to be higher because of the polarity of the source. You have positive and negative. That means here you have lower voltage and here you have higher voltage. That means you will gain the voltage V2. When you cross V2 and get to node C, you will gain voltage V2. So you're going to add that plus V2. All right, now we move through R2 and we get to node D. Is the voltage going to be dropped or it is going to be raised when I move through R2? It is going to be dropped because I'm moving in the same direction as the current is moving. So the voltage at node C will be higher, and then some voltage will be dropped in R2 when current will pass in through this direction, and the voltage at D is going to be lower. That means I'm going to lose some voltage, and that voltage that I'm going to lose will be I2 times R2. Okay, now what about I cross V1 and get to node E? Am I going to lose some voltage? Am I going to gain some voltage? I'm going to lose voltage in this case because of the polarity of V1 and the direction in which I'm moving. I'm moving in the direction opposite to the polarity of V1. So the V1 has lower voltage on the negative side and higher voltage at the positive side. And I'm moving against that direction. So I'm going to lose voltage V1 when I get to node E. And finally, when I get to node A, and I pass through R1, am I going to lose some voltage or gain some voltage? Yeah, there can be two answers, lose or gain. Based on what? So based on your movement and the movement and the movement of the current through that resistor, right? So the movement of the current through the resistor is from node A to node E, and you're moving in the direction opposite, of course. So when you get to from node E to node A, you have gained voltage because node A has higher voltage than node E, since the direction of current I1 is from node A to node E. So when current is going to pass through R1, some voltage will be dropped in R1. That means node E will have lower voltage as compared to node A because of the direction of current. That means when I get from node E to node A, I am going to gain voltage, and that voltage is going to be I1 times R1. And this way, you will know what is the voltage at node A. So you go through each component. You basically observe when you cross that component, when you pass through that component, and get to the node. The next node, is the node voltage be higher than the previous node or lower than the previous node, and then just write down the equation. And basically, you are doing KVL. You're applying KVL basically. You're adding up all the voltages along the way. When you get to the destination, then all the voltages are either added up or subtracted based upon the direction of the current flow through that component or the power supply or whatever. And you get the node voltage. This comes really handy if you have, again, a big circuit and you need to know, you have the values of current, you have everything, and you need to know a specific value, voltage value at any node. Then this method comes very handy that, oh, I know everything. I just have to traverse a path to that node from a known voltage, generally from the ground, and then add up all the voltages along my way, and I will know the node voltage basically. So when you have a big circuit, this method comes very handy to find the node voltage of any point, given that you already know other quantities, current and all those things. Any question about this? So there is something that I wanted to discuss last week. Of course, we did not have time last week, but yes. Yeah. So again, this is, you're traversing a path, right? Node D, irrespective how many branches are there, node D will have a specific voltage, right? The voltage at node D is going to be 1 voltage, whatever. It can be connected to 10 different branches. You just have to traverse one path towards node D and calculate all the voltages along the path, and you will know the voltage at node D. Yes, you can have, as I showed, there can be another branch here, there can be other branch here, but the node voltage is not going to change based upon how many branches are connected. Node voltage will still be the same. Right? So you just have to traverse one path getting to that node. That's it. And add all the voltages along that path. Yes? What is I3? I2, yeah, so this is I2. Yeah, I'm showing I2 again because I'm saying that this is the same branch. So I2 passing through R3, I2 passing through R2, I1 passing through R1. So that's negative I2 R3 from that. Okay. So that is your node voltage calculation. And of course, we discussed DC power last week. The second problem that I gave you, DC power. Again, DC power is going to be always absorbed in the resistor. Of course, resistor always drop power. But as far as power supplies are concerned, power supply can either supply power or absorb power, as we saw last week. And problem number 2, one supply was absorbing power, and 2 supplies were supplying power. And it is very easy. If the positive current is coming out of the positive side of the battery, your supply power supply is supplying power. And if the positive current is entering into the positive side of the battery, then your supply is absorbing power. Okay, so the next topic is discussion of dependent sources. Now, some of you, actually quite a few of you, dependent sources. Quite a few of you who finished 2035C, you guys discussed dependent sources. In the DC and AC courses, dependent sources were not discussed. So just a quick review of dependent sources are. Dependent sources basically are electronic components. They are circuits actually. They're not like individual sources like you see power supply, you have a DC source, a battery, a DC source. So dependent sources, basically they are circuits, but we represent them as sources. They are represented in diamond shape. Again, many of you must be familiar with that. So anytime you see a diamond shape, that's a dependent source. And it can be a voltage dependent source, or it can be a current dependent source. So this is a voltage dependent source, and the other one is the current dependent source. Now, dependent means that their value depends on some factor in the circuit. For example, amplifier, right? What is the function of an amplifier if you have a voltage amplifier? What is the function of voltage amplifier? Some voltage is coming in, some voltage is going out. The output voltage in general is higher than the input voltage, right? Shape is the same, but the output voltage is higher. That is an example of a dependent source because the output voltage is depending on the input voltage. Input voltage is multiplied by some factor, which is the amplification factor, and the output voltage is generated. Now that's the circuit basically. Integrated circuit, we create those circuits. Op amps and stuff, basically, they are voltage amplifiers. So that's a dependent source, which is a voltage dependent voltage source. So there are two dependent voltage sources. The first is voltage controlled voltage source. And the common example is a voltage amplifier. And that source will simply be given by, let's say this is a voltage dependent voltage source, and the source is represented by, let's say, VD, the value of the source, and VD will simply be equal to A times, let's say the input voltage is V input. Then the value of the dependent source will be A times V input, where A is the amplification factor. So that dependent source is called voltage controlled voltage source. A voltage is going to be, input voltage will be controlling the value of this dependent source. And likewise, we can have current controlled voltage source. It's a voltage source, but some current is controlling its value. So the second type of dependent source is current controlled voltage source. So again, it's a voltage source, dependent voltage source, VD, but the value of that voltage source is controlled by some current, let's say I input, let's say I is I input. As the current is coming in the circuit, and the output voltage is depending on the value of the current that is coming in the circuit multiplied by a factor B. So that is what a current controlled voltage source it is going to be. And likewise, we have two current sources. These are two voltage controlled voltage sources. or dependent voltage sources. And now we have voltage controlled current source. So it's a current source, the last one, it's a current source. But the value of that current source, let's call this ID, dependent current source value. The value of that current source is depending on some input voltage. And that's actually your MOSFET, metal oxide semiconductor field effect transistor. Usually your MOSFET falls under voltage controlled current source, where the voltage that you apply on the gate and the source, the gate and the source terminal, between gate and the source terminal, it controls the flow of current from the drain to the source. So that is an example of a MOSFET, electronic component. Did you guys take semiconductor devices already? So you guys discuss MOSFET and stuff, right? And it is represented again by a diamond with the current symbol, and the value of the current depends upon a voltage. And finally, the last one is current controlled current source. And current control current source, basically your bipolar junction transistor, that's an example of current control current source, where the current which is at the base of the transistor, BJT, controls the flow of current from collector to emitter. So current control current source, let's say again ID, it depends upon D times I input. And BJT is an example. Base current controls the flow of current from collector to emitter. So these sources are dependent sources. They are not independent sources. Independent sources are the one that you can just change the value, for example, here, and then you can control whatever voltage they're generating, whatever current they're generating. The value of these sources depend upon voltage or current that is generated in some other part of the circuit. So if that value changes, the value of this source is going to change as well. You cannot really control it because it is dependent on other factors. That's why they're called dependent sources. So we have independent sources and dependent sources. Dependent sources are basically circuits or devices, electronic devices or circuits, but they are used as, as sources in circuit analysis. So let's now solve some circuits, and we're gonna just review mesh analysis now. There are 3 cases of mesh analysis. And let me do each case quickly before. Let's do with independent sources first, and then we go to the dependent sources. So let's say, let's call this problem number 1 for today. And this is case number 1. What is case number 1? That you have basically independent voltage sources. In different branches. So similar to the problem that we did last week. So you have independent voltage sources in different branches, V1, V2, V3, R1, R2, R3, R4, let's say this is 100 ohm, 500 ohm, 700 ohm, and 1 kilo ohm. 10 volt, let's say 22 volt, and 30 volt. Now, if I give you the circuit and ask you again, choose the easiest method to solve the circuit, which method are you going to choose? One by one. Yes. You're going to choose mesh? Okay. That isn't. You're going to choose node because there is one node, so you will have one equation, right? Right now we're doing mesh, right? Right now we're doing mesh, so we have two meshes or two loops. But if you have to choose the easiest method, you must choose nodal analysis because you have only one node here that has unknown voltage. But let's do the mesh analysis or loop analysis. Anybody know the difference between mesh and loop, by the way? Anyone? Did anyone tell you ever what is the difference between mesh and loop? Say it again. Mesh is what? No. Mesh and loop. What is the difference between? Because we say loop analysis or mesh analysis. We say it interchangeably, but mesh is multiple loops. Okay. I think you're on the right track. Yes. Okay. So if I remember correctly, again, I usually forget about it, but what you said is close to, I think it's correct. Basically, loop can have, or mesh, one of them, it can have multiple loops inside, or if you can have a big mesh with multiple loops inside. So one is individual, and one can have more like loops inside or meshes inside. I don't know which one is what, I forget usually. But you can have, like in this case, you can say, oh, I have two loops. But if I go and calculate and make this my big loop, then I have two meshes inside that loops, basically. So that's, what is it? Yeah, exactly. So that's what I'm saying. I usually forget about that. But that's the general difference. But we usually don't really care. And we call mesh and loop interchangeably. That's, again. But there's a difference. Okay, so if I want to write down, if I'm applying mesh analysis on this, by the way, I won't. If I have to solve this circuit, I will never apply mesh analysis. I will always apply nodal analysis because I have only one node for which I will write the equation. But in case you're applying mesh analysis, what will be the equation for KVL and mesh analysis in loop 1? And again, before you apply KVL, remember you always have to mention in which direction the current is flowing. And you can choose any direction, doesn't really matter. Let's go. I just chose the same direction, clockwise, sorry. What will be the KVL equation for loop 1? Okay. Okay. So I'm going to write down. Okay. So I'm going to write down V1 minus V2 equals I1 R1 and plus. Very good. I1 minus I2 R2. So make sure when you're writing the equation for any loop, you go with the direction of current in that loop. So if the other loop, if it's a common branch, like in this case, R2 is in the common branch. If there are two currents flowing through the common branch, then the loop that you're writing the equation for, the direction of the current for that loop is going to be the positive direction. So if the other direction is opposite, that will be considered as the negative direction. If the other direction is in the same, of course, it's going to be same direction, and you're going to add both currents together. So it's going to be simply negative V1 plus I1 R1 plus I1 R2 plus V2 and minus I2 R2 is equal to 0. I usually write down, voltage sources on one side and current drops on the other side through the resistor. So it's the same thing. And what about KVL in loop 2? Always use variables. Yeah. Okay. So V2 plus, because in the same direction, so V2 plus V3 equals. So, all right, so let's just start with this. So I2 times R2, R3, R4. So let's write this down. I2 times, and we can simplify this as I1 times R1 plus R2 minus I2 times R2, because we are writing the simultaneous equations. So of course we are solving for I1 and I2. And for this one, I2 times R4, R3, and R2, R2 plus R3 plus R4, and then I1 is passing through R2, and the direction of I1 is opposite to the direction of I2. That means it will be considered as the negative current, negative I1 times R2. Now, everyone can write this equation without making mistake. Yes, I want to make sure. If you can't, if you have a question, please ask. Because if you make a mistake here, then of course everything is incorrect. Yes. Yeah, because look at the direction of I2. I2 is this direction. That means it is entering into, it is coming out of V3, it is coming out of V2, right? So both voltages are, the current is passing through both voltages in the same direction. In here, I1 is coming out of V1, but it is entering into V2. That's why those two sources were in the opposite direction. And that's why we put V1 minus V2. And again, if you cannot write this, just write with the polarity where current is entering and leaving, just write down the polarity. So for example, if I am writing the equation for this, that's going to be negative V3, negative V2 plus plus I2 R2 plus I2 R3 plus I2 R4, and then the current is going to be coming down. So it's going to be negative I1 R2 is equal to 0. And once you write down, you take the voltages on the other side of the equation. That's going to become V2 plus V3. Rest of the equation is going to be the same. So whichever way you want to write, just make sure you be consistent with the signs, because if you make a mistake with the sign, then everything is going to be incorrect. And at this level, again, this is pretty much review. I want you to have good understanding of this so that you don't make any mistake in the basic KVL, KCL, nodal, and mesh. And once you have this, all you need is your MATLAB and solve for I1 and I2 and do whatever you want. You can calculate power, you can calculate this, you can calculate that. So let's open MATLAB. Let's increase the font size so everyone can see easily. All right, so let's go and put down the values first. So V1, and I want you to do work with me here. Don't just look at it. Work with me so that you can get practice. And then if I do make a mistake somewhere, at least you can tell me that I made a mistake. So don't just look, work as well. So all the values. And then I'm going to write down, I'm going to solve using matrix inversion method that we did. So my matrix A is going to be R1, right here, R1 plus R2 and negative R2 from the first equation, R1 plus R2 and negative R2. And the second row is negative R2, negative R2, and R2 plus R3 plus R4. R2 plus R3 plus R4. So that's my coefficient matrix, coefficient of I1 and I2. And my constant vector on the other side is V1 minus V2, first row, and V2 plus V3, second row. That's my constant vector. And now all I need to do is to use matrix inversion and calculate current. So my currents are matrix A. Remember, I told you backslash can be used as well when you are performing the inverse of matrix. When you're performing the operation inverse of A times C, you can also use backslash, or you can just do INVA times C. And your currents are, let's put down in engineering format. So format short ENG, that's going to give us current. The first one is negative 373.83 microampere, and the second one is 23.5514 milliampere. So let's go ahead and let's just copy and paste. Control C. Control V. So this is my, oops, this is my I1, and this is my I2. Let's delete this. Negative 373, or just let me give both of them in milli. So negative 0.373 or 374, we can say 374 milliampere, and this is going to be what is it, 23.5 milliampere, 23.5 milliampere. Of course, in engineering notation, we prefer to use milli, micro, and stuff instead of exponent -4, exponent -2. So these are my two currents. What is that? I don't know what you're saying. Right. Yeah, I mean, when you have simultaneous equation, all you have to do is to use, of course, matrix inversion method and create the coefficient matrix of the unknown variables on one side and then the constant vector on the other side. Remember, basically you are writing. So basically you're writing A times I is equal to C. I is equal to A inverse of C. That's what the operation is, right? So this is the first case of mesh analysis in which you have independent voltage sources in whatever branches you have. You can have as many independent voltage sources as you have, but that's a very simple case, simplest of the case. The other one is simpler actually. Okay, what is the second case? Any question about this, by the way? Again, ask me question at any time if you're confused or something. I know this is your exposure. I don't think in the previous circuit classes you have used MATLAB or anything to solve anything. So you're gonna develop habit of using MATLAB, and believe me, once you are done with the class, you will love that, because I last time when I taught fall 2021, all those students, they still say, man, the things that we learned, then how you use MATLAB to facilitate problem solving process. Remember, it's the problem solving, right? You still have to analyze the circuit, because you're writing the equation. If your equation is incorrect, MATLAB cannot make it correct. So equation must be correct. That means you still have to analyze the circuit properly. But once you analyze it and then put the equations or do whatever, then solution is not a problem. You can use calculator, you can use whatever. This is just easier. To me, it's very easy to use MATLAB to solve the problem. But you still have to have the art of analyzing the circuit and put down the correct equation and all those things. So this is basic thing. If you do this correctly, this is nothing. This is nothing. You just have to develop the habit of using this. That's about it. But this is the main thing. Okay, any question about this again? Anything that you did not understand in the equation writing or the MATLAB work? MATLAB work, of course, you're going to do. Yes. Okay, let me bring up my window. Okay, here. Compare your work with my work.
Or if you put semicolons, you hide.
After. No. What Lazar is saying, you're not getting anything means you're not. It's not displaying anything. You're saying, right? You may have a semicolon after the command. Oh, you're writing it in the editor. You're not writing.
I'm supposed to write the whole thing in here.
Well, that's what I'm doing. If you want to write it in the editor, that is fine. But then you have to save it and run it.
I mean, I saved it and ran it, but oh, how it works?
Yeah, you have to save it and run it. If you're writing in editor, yeah. Mm-hmm. Yeah.
Oh, okay. So just put format short in there.
Yes.
Your semicolon pathway, and then look at the polarity signs, and that will give you.
Yeah.
Okay.
Yeah. So look at the current direction, and if it is coming out of the voltage source, then of course it's going to be positive voltage. If it's going into the voltage source, it's going to be negative voltage.
Gotcha.
Okay. So let's do one more problem, and then we can take a break since we started, 10 minutes late. So it's only 1 hour right now. So the second case number 2 of mesh analysis is what? You have a current independent source in one of the outer loops, one of the outer branches, not loops. That's the second case. You have a current source in one of the outer branches, or current sources in outer branches. Example of this. So let's say you have let's say you have this circuit, and let's assume this is a voltage source, V1, let's say 100 volt. This is R1, 100 ohm, R2, 300 ohms, R3, 400 ohms, R4, 900 ohms, And let's say this is a current source. And let's call it um, I. Let's call it I source. And let's say this source is 0.10 milliampere. Let's call this source to be 10 milliampere. 10 milliampere. And R5 is 1K, R6 is 600 ohms. So let's assume this is my circuit. I have 3 meshes, 3 loops, whatever you want to call them. The only difference is that I have a current source, but this current source is in one of the outer branches. It's not shared with any other loop. Outer branch means the branch that is not shared with any other loop. So if that current source would be here, then that's not an outer branch. That is shared between 2 loops. And that's the third case that we're going to discuss. Now, this is very simple. Anytime you have a current source in one of the outer branches of any loop, the loop current is equal to the source current. So you already know the current of that loop or mesh, whatever you want to call it. So if we have 3 meshes or 3 loops. You have 1, 2, and 3. So if I assign currents, let's say if I assign current I1 here, I assign current I2 here, and I assign current I3 here. In this case, we already know that I2 is equal to IS because my IS is in the outer branch of loop number 2. So the loop current will become equal to that source, the current source. And if you take the loop current in the opposite direction, opposite to the source direction, then it's just going to be negative. I2 will be negative IS in that case. So that will leave you to know two unknown meshes, mesh number 1 and mesh number 3. That you don't know the current of mesh number 1 or mesh number 3, but you don't have to figure out, you don't have to write down 3 equations in this case. You only need to write down 2 equations for mesh 1 and mesh 3. Don't write down the equation for mesh 2 because you already know the value of that current. So once you know the value of any current, you don't write down the equation for that mesh. So in this case, for mesh 1, what will be the KVL for mesh 1? V1 equals plus R2, okay? Minus I3 R1 because I1 and I3 are in the opposite direction. So minus I3 R1 and plus I2 R2 because I2 is in the same direction as I1. Okay, and we already know what I2 is, so this is known now. So this is 10 milliamperes times R2, which is 300 ohms. So this is a known factor. That means it's going to be a constant. It's going to move to the other side. Unknowns are going to be on one side, and knowns are going to be on the other side. So I have 2 unknowns only, I1, R1 plus R2 minus I3, R1, and my known values are V1 minus I2 times R2. And that will be my equation number 1. Right? Again, if you're confused, make sure you ask questions. Don't hesitate to ask questions. And then mesh number 3, we don't have to apply KVL on mesh number 2, remember, since we already know the voltage, we already know the current in mesh number 2. So mesh number 3, what will be the equation for mesh number 3? And no, I3, you said I3 times R5 plus R6, but I3 is passing through and R1. It is passing through all these 4 resistors. So I3 times R1 plus R3 plus R5 plus R6. All right, what else? Minus I1 times R1. What else? Okay, so I2 is going through R3 in the same direction as I3. So the same direction, that means the voltage drop across R3 is going to be from this side to this side, or in the same direction as I3. So that's going to be plus I2 times R3, and there is no voltage source, so it's equal to 0. And since we know I2 and R3, that is going to be our constant, so that's going to go on the other side. I1 R1 plus I3 R1 plus R3 plus R5 plus R6 equals negative I2 times R3. And that's going to be our equation number 2. Again, make sure if you're writing it, you're understanding it. Don't just copy it, write it once you understand it. Look at the circuit, look at the equation, and if you have questions, then ask. And be very careful when you're writing the equation and you have multiple resistors in different loops. You have to, you know, you have to consider each resistor in the equation. Looks good? Okay. And again, we have 2 equations, we have 2 unknowns. We're going to do the same thing like we did in our last one and solve it. So let's bring MATLAB and let me clear this. CLC, let's put the new values there. Okay, so my V1 is equal to 100. And my I2 is 10 milliampere. R1 is 100. R2 is 300. R3 is 400. R5 is 1K. And R6 is 600, right? Did I miss any? R1, R2, oh, what is this? 300. R3, R4 is missing. Where is R4? R4 is right here, 900. Okay. So R4 is 900. Although R4 is not in the equation anyways, in the 2 equations, because we already know I2. So we did not write the equation for this loop. So even if I ignore R4, it doesn't really matter because it's not in the equation. It's not in the 2 equations. All right, now create my coefficient matrix A. A is, all right, first one is R1 plus R2. R1 plus R2. And then for I3, I have negative R1, negative R1. And my second row is negative I1 R1, so negative R1. And R1, R3, R5, R6. R1 plus R3 plus R5 plus R6. So that's my coefficient matrix of I1 and I3. And let me just keep format showed. And my constant vector on the right hand side, my C is from equation number 1, V1 minus I2 R2, V1 minus I2 times R2, and my second is negative I2 times R3, negative I2 times R3. So this is my constant vector. So my current values are A backslash C, and these are my current values. Let's copy it, and then I'll paste it here. Yes. That's my I1, and that's my I3. And this is going to be what? 244 milliampere, right? Or 0.244 ampere or 244 milliampere. So 245 milliampere. And this is going to be 9.76 milliampere. 9.76 milliampere. So these are my two currents. Yeah, C is your constant values on each side of the equation. V1 minus I2 R2 and negative I2 R3. V1 minus I2 times R2 and negative I2 times R3. So again, don't forget why we are writing this, because we have A times I is equal to C, where C is the constant vector from each equation. I, of course, is the matrix. So this is 400, negative 100, negative 100, and 2100. This is A times I1 and I3, that's the constant vector, is equal to C, which I calculated to be 97 and negative 4. 97 and negative 4. So this is basically your matrix for the coefficient matrix multiplied by the current vector is equal to the constant vector. And from that, you are calculating I1 and I3 by taking A on the other side, taking the inverse of A, and then multiplying it by C, matrix multiplication. I is equal to A inverse times C. So that's the operation we are doing. I don't want to show it for every problem. You guys know that's what we are doing. That's why I just jumped right into MATLAB. But if you have to show, if you have to write down and show, this is how you're going to show basically what we are doing. Okay, let's go ahead and take a break. And we're going to discuss the third case of mesh analysis, and then we are going to introduce the dependent sources in the circuit, and then solve some more problems. The more problems we're going to solve, of course, the better it is going to get. So let's save this thing first before it. Come on, save it. All right. And if you want to look at the MATLAB work, then MATLAB work is here. So I'll see you in about 10 minutes, maybe. Mm-hmm. All right, guys, let's start. So before we move on to the third case, let me go ahead and ask you this: if I want to calculate power from any source, let's say I want to calculate the power from the current source IS, how I'm going to do that? I'm going to do what now? Voltage? Uh-huh. Voltage in the in that whole branch, or no, not R4. Otherwise, the power is going to be the power that is consumed in R4. If you want to find the voltage across R4 and calculate the power using that voltage, then it's going to be the power consumed in R4.
The current times the voltage drop across.
No, that's what he said. But that's incorrect though, because if you use the voltage across R4, that means you're calculating the power in R4, right? Consumed in R4. Yes. But that's then going to be the power consumed in the loop. I'm saying only the power supplied by IS or consumed by IS, whatever. How are you going to do that? Okay, that's one way to go, I would say. Hard way to go, but one way to go. Anyone else? Easier way to find the power either supplied or consumed by IS. What do you need for power? If you have a source, what two quantities you need to calculate the power of that source? You need voltage and current. What do you have? What do you need? So you need the voltage across that voltage source, right? You need the voltage across that source to calculate the power supplied by the source. How are you going to calculate the voltage of the source? That's another question then. So I want to calculate, let's say, Vs, which is across Rs. How I'm going to do that? Okay. All right. How about using the node voltage method that we just discussed? Can we do that? Since we know all the current values, we know all the resistor values, can we calculate the voltage that is, because assume that the bottom is ground, let's say this is ground. Can we calculate the node voltage here? And that will be the voltage, of course, across the source. And once we know that node voltage, we can calculate the power, right? So you can choose one path to get to that node. You can start from ground because we know the voltage of the ground, right? You can start from ground, or you can start from this node because we know the voltage of this node. The voltage of this node is what? 100 volt, right? So you can start from here, you can start from here and traverse a path that goes towards this node where the voltage is Vs. Yeah.
When it comes to, because I think to choose that node because we know the voltage there, would it be really complicated to choose the node that's right above or the?
You don't know the voltage at that node. What is the voltage at that node? You need to know. You need to choose a node for which you know the voltage, because that's your initial value. Now, you always know the voltage of ground. You can always start from the ground. That's given. But if ground is far and there's a node that is close to the point at which you're trying to find the voltage, and you know the voltage of that node, then I would rather start from that node. in this case, if I go from ground and if I take, that path, then, perhaps that might be easier for me, or it might be the same if I go from here. So let's say if I start from here, so basically we are applying KVL, remember. We are applying KVL and calculating, adding all the voltages around this loop. So if I take this path starting from ground and I add all the voltages, then that will be the voltage at node Vs. Like we did earlier, right? I showed you how to go from. So what will be the equation? Let's where should I write, since I want to see the circuit as well. It will be so let's see, voltage across Is, that is Vs. So let's calculate. Okay, start from ground and tell me what the equation is going to be if I start from this point. When I pass R2, what will be my equation when I pass R2? At this node right here, what will be the voltage at this node? No? Look at the direction of current that is flowing through R2. I1 and I2 both are flowing from top to bottom. Yeah, so you have a higher voltage over here, right? You have a higher voltage over here. So if I'm going from ground to this node, I have a higher voltage at this node, and that voltage is I1 plus I2 times R2, because I1 and I2 are flowing through R2. Make sense? Right? So it's not negative, it's positive. So I1 plus I2 times R2, that's the voltage at that node. So I'm going to write down first I1 plus I2 times R2. All we are doing is we are applying KVL in this loop. So basically we are, negative Vs plus whatever voltage here plus whatever voltage here plus whatever voltage here equals to 0. That's what we are doing. I'm just writing it in a different way. All right, when I get from this node to this node right here, what is going to be the voltage that will be either dropped across RS, or you're going to gain in RS? Am I going to gain the voltage, or the voltage will be dropped? I'm going to gain the voltage, because I3 and I2, which is flowing through R3, is going in this direction. So the voltage here is higher and the voltage here is lower. So that's going to be I3 plus I2 times R3. I2 plus I3 times R3. Okay, and the last one that is left is R4. When I go from this node to node here, which is Vs voltage, am I going to lose voltage in R4, or I'm going to gain voltage in R4? No? I'm going to lose voltage, because current is flowing in this direction, right? So the voltage here is higher and the voltage here is lower.
I think the confusion might just be coming
Yeah.
in because, like, for example, when I'm writing it, I put the polarities, plus minus, things like that.
Yeah.
Since it shows that arrow that you have there going up and then to the right and then down.
Yeah, but okay. So polarity is fine, but you need to understand the concept, right? The current, if the current is flowing in a resistor, where current enters, you have higher voltage. Where current leaves, you have lower voltage. As simple as that, right? So the current that is entering in R4 is Is or I2. It is entering from here and exiting here. That means this side has higher voltage and this side has lower voltage. So when you pass from here to here, you are going to gain voltage in R4. It's not going to be dropped. It's going to be voltage gain in R4, because voltage here is higher and voltage here is lower. Yes? So again, so I'm going from the top node right here, and I'm moving to this node. And the current in R4 is going from top to bottom, bottom to top, right? So the voltage that will be dropped in R4 when the current will pass through it will result in a lower voltage at this node. So I'm going from a point that has a lower voltage to a point that has a higher voltage. So I'm gaining voltage. That voltage is the voltage that was dropped in that resistor R4. I gained that voltage when I went through that. So that's going to be I2 times R4 plus I2 times R4. And that is going to be your voltage at Vs. Now, if you apply KVL in this one, apply KVL, that's fine. Negative Vs, positive I2 times R4, positive I2 plus I3 times R3, and positive I2 plus I1 times R2 is equal to 0. That will be the KVL equation, right? And that equation is exactly the same that I wrote. Because negative Vs, when you take it on the other side, is going to become Vs. So basically, it is the application of KVL. The only requirement in KVL is what? Like in the loop, basically you're adding all the voltages. But in this case, when you're calculating the node voltage, what I told you is you can start from anywhere. You don't have to have a closed loop. You can start from any node. All you have to do is to either add the voltage when you go from one node to the other node, or the voltage will be dropped based on the direction in which the current is flowing through that component, or if it's a power supply or something, the orientation of the power supply, where is the positive, where is the negative. So you can start from any node, go to any node, and calculate the voltage. You don't have to have a closed loop, because for KVL application, you have a closed loop, of course. So that's the voltage Vs. We are starting from here. You can start from here. If you start from here, it is going to be what? 100 is the initial value. And then you pass through R1. Then I1 and I3, they're in the opposite direction, right? So I1 minus I3, or you're going in this direction. So let's say you calculated the value of I1 is, so I3 is higher value. That means the actual current is flowing in this direction through R1. Then that means the voltage here is going to be higher, and here it's going to be lower. So when you pass through R1, your voltage is going to be at this node, I3 minus I1 times R1. So you're going to have 100 plus I3 minus I1 times R1, because I3 is higher than I1. And then you move through this R3, get to this node. Both currents are in the same direction. So I3 plus I2 times R3, you're going to gain that voltage here. And then again, you're going to move through this. So you can take any path. Your result is still going to be the same, irrespective, because the node voltage is not going to change. It's still going to be the same node voltage. And you can take any path. All you have to do is to get to that node from any path, and then keep adding the voltages along your way. So we can calculate Vs, which is this. And once you calculate Vs, then of course you can calculate the power. So in this case, Vs is going to be I1 plus I2. Oh, let me just first do I1 is equal to I of 1, because I have a vector, and I3 is equal to I of 2. So the second value of I is I3, and the first value of I is I1. And my Vs is equal to I1 plus I2 times R2 plus I2 plus I3 times R3 plus I2 times R4, I2 times R4. 93.386. 93 point. Therefore, power of IS, it is going to be supplied because voltage is positive, current is coming out from the positive side. So PS is I2 times Vs. 0.9339 or 933.9 milliwatt. 933.9 milliwatt. 934 milliwatt. So that is going to be the power supplied by IS. All right, guys, make sense or no? All right, since we don't have much time, let's discuss quickly case 3 and then at least do one problem with dependent sources as well. We're going to be using dependent sources, other circuits as well. So case 3 is that you have a current source in a common branch. Common branch, that is a branch that is common to between two meshes or two loops. Current source in a common branch. This was problem number 2. Let me call this problem 2. And then this is going to be problem number 3. So let's give you an example. All right, so you have, let's say, voltage source, V1, 100 volt, R1, 510 ohms, R2, 660 ohms, R3, 970 ohms, R4, 330 ohms. Let's say these are 4 resistors. And let's say this is the current source. IS, which is 510 and stuff. Let's say this is 100 milliampere. And this is another voltage source. All right. Now, in your previous classes, if you have a circuit like this, how did you use to solve this circuit if you have to apply mesh analysis? It falls under a special category of circuits. Say it again. Super mesh. Yeah, you used to solve it using a super mesh technique. So I'm gonna show you how you get super mesh. Basically, first I'm gonna do without super mesh, and then we'll do the super mesh. So we're gonna go ahead and do simple mesh analysis. So I'm gonna apply the current I1. I'm gonna apply this current I2. And since mesh analysis requires you to add voltages, and we have a current source over there, not the voltage source, so you are just going to go ahead and assign a voltage Vs across that current source. Because again, when you're writing the KVL equation, it is comprised of all the voltage drops, all the voltages, not the current. So you're going to assign a variable, a voltage supply, Vs, which is across that. Now, when you write down the KVL for loop 1, what will be your equation? What will be your equation for loop 1? Okay. Okay. So V1 equals I1 R1 plus Vs, and all right, so I1 plus I2 times R2. Okay. And I'm going to write this down as V1 is known, of course. So I'm going to write this down as V1 is equal to I1 R1 plus R2 plus I2 times R2 plus Vs. And that's going to be my first equation. Remember, we don't know the value of Vs, it's unknown. So that's why it will stay on the side where you have the unknown variables. All right, what will be KVL in loop 2? What will be the equation for KVL in loop 2? Okay, so V2 equals I2 times R4, R3, R2. So R2 plus R3 plus R4, and okay, very good. So V2 equals I1 times, what was that? R2 plus I2 times R2 plus R3 plus R4 plus Vs. And that is equation number 2. Now we have 2 equations and we have 3 unknowns. So we need one more equation because the number of equations should be the same as the number of unknown variables. Where is that third equation coming from? It is coming from the current source, and what that equation is going to be? Okay, so tell me what equation, what should I write? Sum of both currents should be equal to? No. Not Vs. Vs is not going to be there. No. IS, so you're equating current equals voltage. That is not possible. Current cannot be equal to voltage. No. Vs is not across R2. Vs is across the source. It's not across R2. No, it's not the same voltage. Why it's going to be the same voltage? IS equals I1 plus I2, but there's a mistake in there. The equation, you're on in the right direction, but the sign is incorrect. Why the sign is incorrect? Because they're opposite. So IS equals negative I1 plus I2. IS equals negative I1 plus I2. So that's going to be our third equation. Also, negative, let me write down IS since we know the value. IS equals negative I1 plus I2. And that is our third equation. So now we have 3 equations. We have 3 unknown. We can solve them. Let's go ahead and solve them. And then we're gonna do the same using super mesh. V1 is 100. V2 is 50. Again, make sure you work as well. Don't just look at the screen. R1 equals 510. R2 660, R3 970, and R4 is 330. Okay, so let's go ahead and from the three equations that we have, let's write down A is equal to, from the first one, R1 plus R2, R2, and 1. Coefficient of Vs is 1. Second row, R2, R2 plus R3 plus R4, and the coefficient of Vs is 1 again. And the third row is -1 for I1, -1 for I2, and 0 for Vs, because there is no coefficient for Vs. So that's my coefficient matrix. And my constant vector is going to be, from the first one is V1, from the second one is V2, and from the third one is IS. 100, 50, and 0.1. So let's go ahead and solve for my unknown. Now my unknown matrix in this case is not entirely comprised of V. It is V and I. So I have A times X equals C, where X is I1, I2, oh no, sorry, I1, I2, V. Yeah, that's fine. I1, I2, and Vs. This is these are my unknown X. Current, 2 currents, and 1 voltage. So X equals A backslash C. So, okay. So this is I1. This is I2. And this is Vs. Negative 44.2, negative 44.2 milliampere, negative 55.8 milliampere, negative 55.8 milliampere, and 188 volt, 188.5 volt. So the voltage across the current source is 188.5 volt. And both my I1 and I2 are in the opposite direction because current source has higher voltage than both the voltages of both the voltage sources. So the current is in the opposite direction derived from the current source. So again, once you have all the voltages and the values, voltage, current, and all those, you can calculate power, you can do whatever you want. So this is if you don't apply super mesh. You go with mesh analysis, you don't apply super mesh, all you have to do is to apply a voltage across the source, a variable, and then solve for that variable. It will increase the number of equations, of course. Instead of 2, we have 3 equations. If you're using MATLAB and stuff, it doesn't really matter as long as you're writing the correct equation. Supermesh reduces the number of equations, basically to 2 equations instead of 3. So let's see how we get the supermesh from the same. If you observe, let's see, the middle branch, the voltage across the middle branch is going to stay the same. So you have in the middle branch, you have Vs I1 R1 and Vs plus I1 plus I2 times R2. So look at this. Look at this piece. You have this in the equation number 1. And if you look at the equation number 2, you have Vs I1 plus I2 times R2. So Vs I1 R2 plus I2 R2. This is common in both equations, right? This is common in both equations. And that's what supermesh does basically. From equation number 1, you can write down, if I want to call this my, let's say my variable y, then you can write down y is equal to V1 minus I1 R1. And from the second equation, you can write down y is equal to V2 minus I2 times R3 plus R4. Let me write it down and tell you. From equation number 1, my variable y is V1 minus I1 R1. This is my y. So y is equal to V1 minus I1 R1. And from my equation number 2, I can rewrite this equation to show you. So V2 is equal to I2 times R3 plus R4 plus Vs plus I1 plus I2 times R2. So that is going to be my y. So I just rewrote this equation, and that is my y. I2 times R3 plus R4, I2 times R3 plus R4, Vs, I1 times R2 plus I2 times R2. So from the second equation, my y is V2 minus I2 times R3 plus R4. So I can write down V1 minus I1 R1 equals V2 minus I2 R3 plus R4, or V1 minus I1 R1 minus V2 plus I2 R3 R4 is equal to 0. I can write this equation down. What is the application of supermesh? How do you do supermesh? What do? You ignore the common branch where you have the current, and you write the KVL from the outer loop. So you write KVL in the outer loop, right? All right. So if you write KVL equation in the outer loop, what you're going to get? Negative V1 plus I1 times R1 and negative V1 plus I1 times R1 minus I2 times R3 plus V2 equals 0. Huh? I2 times R4, yeah, R3 plus R4. negative I2 times R3 plus R plus V2 equals 0. All right, look at this equation. And then the one that we wrote, this equation. Both equations are exactly the same. Negative V1 plus V2 plus I1 times R1 minus I2 times R3, R4. V1 minus V2 plus I2 times R3 plus R4 minus IR. Both equations are exactly the same. So this is where the super mesh is coming from, basically. It just equates those values that are in the common branch and create one equation out of that. And the second equation will be the same as our third equation. IS is equal to negative I1 and IS is equal to negative I1 plus I2. So now you have two equations. This is your first equation. You can rewrite this first equation, of course, in terms of V1 minus V2 is equal to I1 R1 plus I2 R3 plus R4. So let's call this equation 4. Let's call this equation 5. So now you have two equations. You have two unknown. You eliminated what? You eliminated the third unknown variable, which was Vs. So now you can solve for the two mesh currents, I1 and I2, and then do whatever you want to do. In this case, of course, if you do want to calculate the power of the current source, then again, you will have to calculate the voltage using node voltage method or whatever, or KVL. In that method, of course, you already know the voltage across the current source because that was our third variable. Right? Negative sign where? Yeah, negative I2, that is correct. Negative I2. Yeah, you're right. Negative I2. So I'm not going to solve it, of course. So you guys, it's the same thing, same values you're going to get. So this is your super mesh. In super mesh, you basically ignore the middle branch, write down the KVL around the loop, and then you write down the difference of the two currents should be equal to IS, or the sum of two currents should be equal to IS or minus IS based upon the direction of the two currents that you are taking. That's your third case. So you have three cases of mesh analysis. Simple voltages. If you have voltage sources, you don't have to do anything. You just apply the KVL and Ohm's law mesh analysis in each mesh. If you have current in the outer loop, then the loop current is going to be the current source. You don't have to find the current of that mesh. And then the third one is if you have current source in the common branch, then that's the super mesh, or you apply the voltage and then solve for that. Okay, so we have about 10 minutes left. Let's do one quick problem. So this is going to be solved to find I1 and I2. This is the super mesh case. All right, so let's do one more problem, last problem for today. And let's introduce a dependent source now. So let's say we have V1 10 volt, V2 5 volt, and let's call this V3, dependent source is V3, and let's say this source R1 let's say this source voltage, let's say this is a dependent voltage source, voltage dependent voltage source, and this source voltage depends on the voltage of across R1. So VR1. Let's say this voltage is 3VR1. Whatever the voltage across R1, that voltage source voltage depends on that. All right. Once again, if I ask you to choose the easiest method to solve this thing, which method you're going to choose? Nodal analysis, because we have only one node. But since we are reviewing mesh, so let's just go ahead and solve this with mesh analysis right now. So that's my current I1 in this. And let's say this is my current I2 in this. KVL in loop 1. What will be the KVL equation? V1. Okay. Okay, well, if you're putting on the other side of the equation, it's going to be plus V2. But if you're putting V1 and V2 together, then that's going to be minus V2. So if you're doing negative V1 plus I1 R1 plus I1 plus I2 R2 plus V2 is equal to 0, then you can manipulate that. But if you're putting both voltages on one side, then that's going to be V1 minus V2 equals I1 R1 plus R2 plus I2 times R2. That's going to be our equation 1. All right, what about equation 2? Yes, equation 2. I'm sorry? V3 minus V2, okay. V3 minus V2 equals, all right, I2 R2 plus R3. Okay, I1 R2, and then I'm going to put plus over here. Okay, and now we're going to go ahead and replace the value of V3 by the value that it depends upon. So that's 3VR1. And what is VR1? I1 R1. So actually this thing is going to be simply 3 times I1 times R1. So we're going to replace its value by that. 3 times I1 R1 minus V2 equals I1 R2 plus okay. Take this on the other side of the equation. So I'm going to have negative V2 equals I1 negative 3 I1 negative 3 R1. Oh, though this is I1 R1 and this is R2. So I1 times R2 minus 3 R1 plus I2 R2 plus R3. And that is going to be equation 2. Right? Make sense? 2 equations, 2 unknowns. Let's go ahead and solve them. All right, question number 1. Oh, first let me go ahead and enter the values of each variable. V1 is 10, V2 is 5, and R1 is 100, R2 is 200, and R3 is 300. And of course, we don't enter the value of V3 because it is in terms of another variable, which we do not know. And now let's go ahead and determine our matrix coefficient matrix from the first one. It is R1 plus R2, the coefficient of I1, R1 plus R2, coefficient of I2 is R2. And from the second equation, coefficient of I1 is R2 minus 3R1, R2 minus 3 times R1. And coefficient of I2 is R2 plus R3, R2 plus R3. So that's my equation, coefficient equation. And my constant vector is from the first one, V3 minus V1 minus V2. And from the second, oops, bracket. And my second is negative V2, negative V2. 5 and negative 5. So my current I is going to be A backslash C. My two currents, 20.58 milliampere and negative 5.88 milliampere. Let's copy it and put it down here. I1 is equal to this, and I2 equals to this. Twenty point 20.58 means 20.6 milliampere, and negative 5.89 milliampere, negative 5.89 milliampere. So these are my two current values, I1 and I2. Current I2 is, the direction of current I2 is opposite to the direction that we have assumed. So it is also flowing in the clockwise direction, not in the counterclockwise direction. Value will be same, direction is going to be opposite because the current value came out to be negative value. So this is how you interpret, you do, basically it's the same method, what you're applying. Even if you have dependent sources, it's exactly the same method. The only difference is that in the equation, last equation, where the dependent source is appearing, you have to go ahead and plug in the equation for the dependent source. And then your number of variables will be the same, two variables, instead of having a third variable for the dependent source, which is 3VR1. So exactly the same method. And again, if you have dependent current source or whatever, you do the same thing as you do with the independent current source. You do exactly the same thing. If you have dependent current source in the outer branch current will be the same as the current of the dependent current source. If you have in the inner branch, you can still apply super mesh, basically. Okay, guys, and that is about it for today. I think we are on track. We discussed dependent sources, mesh analysis. We did one problem with dependent sources, but we're going to do some more problems next week, hopefully. I will see, I believe I may post a homework from whatever we have done this week. So make sure work on the homework, and perhaps expect that there will be a quiz next week then, since I'm assigning you a homework. So it's all practice. Make sure you solve as many problems as you can. Whether I'm assigning them, well, you have to solve the one I'm assigning them, but from the book, just pick problems and solve problems. That's how you get better with circuits. That's what I did when I was undergrad. Just went to the book, and go to the end of the book and just start solving problems. You get stuck somewhere sometime, yeah, that's normal, but at least you get practice. And if you get stuck, then you ask that, hey, I'm doing this problem and I'm getting stuck. Then you seek help, basically. Ask me, go ask in the open lab, ask me, and then that's how you're gonna get good at solving circuits. I think everyone is here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think the guy who didn't come, he dropped the class, so we have only 10 students. Yes, you were asking something? Yeah, I can see that you're here, of course. Yeah. Okay, so everyone is here, everyone is present. I will see you guys next week. I'm gonna post this lecture, as well as I'm gonna post the recording of the class that we are doing today.